All right, so one final example of conservation of momentum. This one adds the complexity of a non-uniform flow profile. So here's the problem statement. It says that we're going to be given a segment of a pipe. There's a whole pipe going on here, but we're just going to look at this one little segment of it. Going in is a uniform flow. We don't know the velocity, but we do know the mass flow rate. Going out is this non-uniform profile because friction has done its job over the course of this pipe. And so we get this non-uniform profile, but they've given us the equation of that profile as a function of radius, and they've also given us the radius of the pipe. There's an anchor force, which they've measured and told us the number. There's a length, gravity points down, and z is going to point upward. And we're asked for two things. First off, in this equation for the velocity profile, what is W max? And then number two, what's the pressure change over the length of the pipe? So when I see something like this, W max, where we're looking for velocities related to each other, that's usually an indication that we should start with the conservation of mass to work this out. But when I see pressures and I see forces, right, pressures are essentially just forces per area, forces, that tells me that I want to deal with the momentum. And so it's going to turn out we're going to need both of these, but let's start with solving for W max using the conservation of mass. Conservation of mass. And so we have d by dt integral over the volume of rho dv plus the integral over the area rho v dot n dA equals 0. We've got a couple simplifying assumptions here. We're told that it's steady. That lets us get rid of this term here, steady. Since it's now equal to 0 and we're told it's incompressible, density pulls out of the integral and can divide away because it's incompressible. So now we have to deal with this, which we can't do until we define a system. So real quick, let's define a system as the boundary just inside the pipe here. We're going to have a couple normal vectors, right? We've got our normal vectors always point out, so n2 points this way and n1 points that way. That's going to be very important in this problem, it turns out. And that lets us write all of our velocity vectors and dot products out real quick, right? We can write v1, which is equal to the velocity coming in here, which since it's in the z direction, we'd call w1 as its magnitude, and its direction is straight up and down, which is k hat direction. And n1, of course, is pointing down, so it's the opposite of that, right? So v1 dot with n1 is going to equal w1 times k hat dotted with minus k hat, which is equal to minus w1. And then we have v2, which is coming out this way. And so that's got this thing w2 as a function of r times k hat. It's still pointed in the vertical direction. And so v2 dot n2 is going to equal w2 of r times k hat, and all of that then gets dotted with k hat. And so k hat dot k hat's just 1, and so we're left with w2 of r. And just to clarify what I'm writing here, when I write this, I mean of r, as in as a function of r. It's not w2 times some little r. So let's make those substitutions into the conservation of mass, and where we'll end up is the integral over a1 of minus w1, that's v dot n1, minus w1 dA plus the integral over a2 of v dot n2, which is w2 of r dA, and that's equal to 0. Well, now we got a problem, right? This is a function of r, which means we actually have to do the integration, which means we need a differential area. Remember, this is a circular pipe, and so our differential area is the little wedge, which is given by r d theta dr. And we can sub in the definition for W2 as a function of r that they gave us. Let's go ahead and do this integral, because that's the simple one, right? This is just minus W1 A1. The second integral, though, we're actually going to have to deal with. So we'll sub in here. The equation they gave us was 2W max times 1 minus little r over big R squared. And all of that was times now our dA, which is r d theta dr, and it's got to be equal to 0. All right, so to avoid rewriting a bunch of stuff, let's just deal with this integral for the time being. First off, we need some limits, okay? The theta is, if we're going to do a full circle, is going to go from 0 to 2 pi. And the radius, since this is not annular, it's a full circle as well, so it's just 0 to capital R. So first off, the 2 and the W max can come out. So we can pull those out to W max. And now we have two integrals here, right? The 1 and this r over r squared, but there's this extra r here. So when you distribute that, we're going to get the integral from 0 to r, 0 to 2 pi of r d theta dr. And we're going to subtract from that the integral from 0 to r, 0 to 2 pi of r per r squared times r d theta dr, just as that integral. All right, we can do the theta integral pretty easy because there are no thetas in here, and so the theta integral just becomes a 2 pi, and so I can write this as 2 W max times 2 pi integral 0 to big R of little r dr, and we're going to subtract from that, pull all the constants out of here, so the integral again gives us a 2 pi, that's the integral of theta. This capital R is also a constant, and so I'm going to just go ahead and pull that out as a cap R squared, and we're now left with the integral from 0 to capital R of R squared here plus this extra R gives us an R cubed dr. Okay, so now we can integrate these with respect to R. 2 W max, we've got 2 pi. Now the integral of r dr is just r squared over 2. Sub in for 0 and cap r, that just gives us a r squared over 2. Now minus, we got 2 pi over cap r squared. Integral of r cubed is r to the 4 over 4. Again, subbing in for 0 and capital R gives us an r to the 4 over 4. With a little bit of algebra, this just becomes 2 W max times pi r squared over 2. And so you might be seeing something here, right? These 2's cancel, pi r squared, well that's just the area. And so we can now bring in the rest of the actual equation here as W1 A1 plus W max times A2, and that's equal to 0. So that's our simplified version of the conservation of mass. But keep in mind, this is just a straight piece of pipe. And so there's only a single value for the area really. A1 is equal to A2, which we're just going to call the area, just call it the area A. Okay. Now we need just a couple more inches here, so I'm going to move to a new page and reuse some of what we just solved for. Okay, we'll just keep that up here. Just for reference, we had 0 is equal to minus W1 times the area plus W max times the area. That's the conservation of mass, and what it tells us is that W max is actually equal to W1. Well, that's great. We'd be done if we knew W1, but we don't. They gave us M dot 1, and so if we did a little audit here, we'd know, well, we still don't have this worked out. But we can use a quick definition to close this out. M dot is equal to rho W1 times the area, which means we can rewrite this to say that W1 is just equal to M dot over rho times the area. Well, that gave us W1. You sub that in here, and it tells us that W max is equal to M dot over rho A. Notice they gave us M dot, they gave us rho, and we know R, so we can calculate the area. And so we have solved the first half of the problem here. Find W max. Now, if we want to find the delta P, that looks like forces, and so now we're going to conserve momentum. So, anytime I see forces, I'm going to conserve momentum. And so that tells us that it's time to write out d by dt of the integral over the volume of v rho d volume plus the integral over the area of velocity times rho v dot n dA, and all that has to be equal to the sum of the forces acting on the fluid. So keep that in mind. Again, our system was defined as just inside the piping here, and we still have N2 pointing up, we still have N1 pointing down. Keep in mind the forces acting on this looks like P2 times an area acting downward. Pushing this way on it is P1 times that area. We also have a gravity force, so I usually indicate that with a little center of mass here. Call this the gravity. The weight is equal to mg. And there's also a shear force going on here, right? Because if it went in like this and it came out like this, that was caused by fluid shear. But here's the thing. That's actually captured in this anchor force that we have. Right? This anchor force is going to be the shear plus the gravity, shear, and pressure all in one. So we get to simplify the conservation momentum here. Again, it's steady. And now we need some vectors real quick, right? We need V1. Well, we already worked this out, but I'm going to rewrite it so you can see it. V1 was equal to W1 k hat, and V1 dot N1 was equal to minus W1, and V2 was equal to W2 of R times k hat, and V2 dot with N2 was equal to W2 of R. And so once again, we have these two areas. We're going to sub all this in, get the sum of forces on the right-hand side. Life's going to be great. So we're going to integrate over A1. Remember, we want the whole vector of V1, so that's a W1 k hat. Then we want rho. Now we want V dot n at 1. Well, that's a minus W1. And all of that is multiplied by dA. Same deal at station 2, A2. Now we have W2 of R times k hat. That's our velocity vector. Then we have rho. Now we need V dot n. Well, that's W2 of R. And then we have our dA, and that's all equal to the sum of the forces. And once again, we have the problem of this being a function of R, and so we have to actually use the fact that dA is R d theta dr, same little pi wedge. let's go ahead and start doing these integrals. Remember, this one, nothing's a function of area, and so we can just integrate it directly as minus W1 rho W1 A1 K hat. And I'd like to point out real quick, rho W1 A1, well, that's just rho VA. That's our mass flow. Okay, so to avoid rewriting things too many times, let's work on the second integral here, which again is going to go from 0 to r and 0 to 2 pi. I'm going to have W2 of r times the k hat times rho times W2 of r times r d theta dr, and all that has to equal the sum of the forces. So, like as advertised, let's just work on this a minute. Okay, first off, rho and k hat are constants, so I'm going to pull those right out. Rho and k hat, they can come right out. We're left with two integrals here, one from 0 to r, one from 0 to 2 pi of W2 squared. Remember, that was a function of r times r d theta dr. Again, notation here, this means function of r. I'm not saying W2 squared times r here. I know that looks a little confusing. So we do that substitution again, right? We got rho, oops, sorry, wrong color. We got rho times k hat times our double integrals, 0 to r, 0 to 2 pi. If we make this substitution, now we won't have any more confusing notation, so let's get there. Remember, this was 2w1 times 1 minus r over r squared, and now we're saying W2 squared, so we got to square that whole business, then multiplied by r d theta dr. A little bit of calculus, right? We got to rearrange and do some integrals. All of this just becomes 4/3 times pi times rho W1 squared cap r squared times k hat. Right, that's just integrating this in two different terms, doing a bit of multiplications and some things. So if we sub all that in, we're left with the conservation of momentum telling us minus m dot times W1 k hat plus a 4/3 times pi times rho times W1 squared times r squared times k hat. That's the two integrals, and that has to equal all the forces. Let's go ahead and get those right. All right, so come back and look at the picture. We got P1 and A acting up. So P1A acting up. Acting down, we have minus P2A minus P2 times A. We have the weight, which is acting down, mass times gravity. So minus mg. And then we've drawn the anchoring force Fz pointing upward. So that's plus Fz. And all of that is in the z direction, so it all gets a k hat. Now I've just barely ran out of space here, so I'm just going to slide this up a little bit. Let's see if I can get away with it. Oh, I can. Cool. We'll finish this problem out real quick. So if we do an audit on this, we know m dot. We don't know W1 directly. We know rho. Once again, we don't know W1 directly. R squared, yep, we got the geometry, so we're good there. We're not told P1. We can get the area quickly enough. We're not told P2. Once again, we know the area. We don't know the mass. Gravity we know, and we're given Fz. So let's start looking through what we can do about this. Well, where could we get W1? Turns out we already worked that out. That was from the conservation of mass, right? Conservation of mass told us that W1 was equal to m dot over rho A, so that fixes that issue. Now, the pressures here, well, that's actually what we're looking for, right? The thing that we were asked to find was delta P. So if we remember that the areas are equal, we can just say this is a new thing, delta P times the area, and that's the thing we're looking for. So put some stars on that, but you know, that's all we're after, so it's okay that we don't know it. It turns out P1 and P2 can be collapsed into a single unknown, which we just call delta P. And then the last unknown is the mass. Well, that's just the mass of the fluid in the tube, which we can find readily enough by doing density times volume, which that's density times what's the volume? Well, in terms of what we're given, it's the area times the length. And so if you take a minute and stare at this, you'll notice that I've taken the conservation of momentum here. I used the conservation of mass to take care of these unknown velocities. I simplified these two pressures into a single thing that we called the pressure drop, and I figured out how to relate the mass in terms of density and volume of our thing. And so, believe it or not, we now know everything we need to know, and with just a little bit more algebra, we can actually rearrange this to solve for delta P, which I'm actually going to do for you right now. So, let's blank all that out, rearrange it real quick. I'm just going to write this out. You should check me, but I'm right. That delta P would turn into m dot squared divided by 3 rho times the area squared plus rho G times L, the length, that's the weight there, plus the anchoring force over the area. This turns out to be everything you need to find delta P in terms of things we're given in the original problem statement.